Good morning, Earth Science. Today we're going to start talking about Chapter 19, which is all about the atmosphere in motion. So, what this chapter is going to be about, what you're going to learn, is mostly things related to wind. So, the atmosphere is constantly moving, clouds are moving in the sky. We've talked about them already. But we're going to talk about how the uneven heating of the Earth creates this movement inside of the atmosphere of different wind belts and kind of some different phenomena there. The first thing we have to talk about is air pressure and wind. So air is a constant force on Earth's surface. It helps to moderate surface temperatures. It feels cooler on a windy day. It helps to distribute moisture and move clouds around. And it helps to cleanse the atmosphere. The thing that sets wind off is this difference in air pressure. So this area that is getting warmed up has air that is rising. This air that is cooling off is sinking down and kind of replacing it. So we need to talk about what air pressure is. So air is, when we talk about air, we're talking about all of this column, all the way up to the thermosphere of every particle. Most of it's in the troposphere, but we're talking about all this column above you when you stand on the planet. So all of this force that it creates on one unit is called an air pressure. Like water, air is exerting pressure in all directions. It's pushing on the sides, it's pushing on the top, it's pushing on the bottom. And air pressure is good. We need it. Without air pressure, we wouldn't be able to breathe. Humans require to have a certain amount of air pressure. As you climb up higher on mountains, you lose the ability to breathe. And that's because that air pressure changes as you get an elevation increase. So as you move upward, you can see in this kind of photo here, these particles up here at the top are less close together. They're farther apart than down at the bottom. So if you are at Mile High Stadium in Denver, Colorado, which is a mile high, about the air pressure that you're getting exerted on you is 82 times less than that at sea level. So if you're standing at sea level, you're getting more kind of air pushing down against you than if you're at Mile High. When you look up and you see a passenger jet flying above you, they are only about 25% of the air pressure that we have at sea level. That's why their cabins have to be pressurized to make sure that your lungs and your body is able to operate as they're flying at that height. Whenever you get a large change in elevation, either up or down, you can feel that change in air pressure. This is why when you're driving down a hill and you can like yawn and pop your ears, this is what's happening there. You are changing in pressure. The inside of your head is still kind of at the old pressure, and so when you yawn, you allow everything to kind of standardize and release and all that pressure to become equal. So we have many different ways of measuring air pressure. We figured out how to measure air pressure in more modern science. So there are lots of different scales for it, a lot of different people trying to kind of claim to it. But the process for how we determined it is kind of what this image here is showing. This image is a barometer, and there are two types of barometers. There's this one, the mercury barometer, and then there's kind of the new one that we invented. But this one, pretty simple. You took a glass dish, you put a tube inside, you filled it with mercury, you put a tube down into the mercury, and then the mercury would flow up the tube equal to the amount of pressure that was available at the time. So mercury is a super dense liquid. It's about 30 times denser than water. So you don't need a very big tube to have a successful barometer made out of mercury. However, mercury is not as safe as other kind of things, so we tend to not use it very much anymore. All right, the second kind here is an aneroid barometer. This is the kind that Mr. Greer has in his classroom, and it uses this metal capsule here to measure changes in air pressure. If there is a decrease in pressure, this whole kind of vacuum chamber in here will expand. If there is less pressure, this thing will shrink in size. This causes this pointer here that's connected via the spindle to move up or down, displaying the air pressure. And then if you were to take this and measure it over a lot of time, it would be a device that is called a barograph. And Mr. Greer has one of those in his classroom as well. So when we record air pressure, we use lots of different units. To measure mercury, we use inches and we use millimeters of mercury to describe this height here. And so we could also say we'll use millibars. And at sea level, millibars is down here at 1,013 millibars. At Mile High Stadium, which is right about here, around 835 millibars. As we move to the top of Mount Everest, we're at right about 100 millibars here. And then as we continue to climb up above that, where these planes are flying, we have a lot less available atmosphere to breathe, a lot less pressure. So what's the cause for this change? There's kind of two things that affect air pressure, and the first is temperature, and that's the more obvious one. And then the second one is humidity. So for temperature, as the temperature increases, the pressure decreases. This hotter air is spreading out and doesn't have as much pressure versus this cold air here that has more units in the same amount of space. So as pressure decreases, air pressure increases. The colder the air is, the more dense it is, the closer together the particles. So we also said that humidity plays a big factor in air pressure. And it does. Changes in how humid something is changes the air pressure. The more water vapor in an air, the lighter the air is. So water molecules are less heavy than oxygen molecules. The reason for this, water molecules are H2O, and oxygen is O2. Oxygen itself weighs around 16 atomic units, and hydrogen weighs, so this is 16 times 2 because there's two of them, for a total of 32. Hydrogen weighs 1, so that's 2 plus 16. So hydrogen weighs 1, but there's two of them. So there was 2, so it's 18. So water is just about half as heavy as regular oxygen. So dry air is 99% oxygen and nitrogen, much heavier elements that are going to want to sink down below it. So they have more pressure. So when we have humidity here, you can see that these are the ones that have the little water vapor H2O. Little blue dots are in this one. This mass is 440, this mass is 420. So even though it's not a very large it's not a large difference, it is significant. And this is why when we have warm, moist air, it wants to go up into the upper troposphere and become clouds. So we can use this information to start talking about forecasting. So changes in air pressure give a simple, it's not always 100%, but it is a kind of way to start seeing some trends in the weather. So a decrease in pressure in a certain area usually means that there's warmer, more humid air there. And this warm, humid air usually makes it up into the troposphere, condenses, and becomes rain or snow, some kind of precipitation. An increase in air pressure, where we're starting to get more air in there, often signals that it's cooler air. The cooler air is usually drier, and we'll usually have sunny weather, where we have these kind of cloudless nights. When we look at maps, we can talk about isobars. These are lines that have the same amount of air pressure. If, like on this one here, this whole area has 20 isobars of pressure there. If the air pressure increases as you move from the outside to the middle, this one's 16, 20, 24. This is called a high pressure area, or a high. Usually it's going to be a cold area. If it's decreasing, 16, 12, 8, we call this one a low pressure area, or a low, and usually that means warmer weather. Looking at the difference, we can make a thing called a pressure gradient. And this is where we divide the pressure over the distance. It's the same thing as like when we were doing topography and we were talking about gradients going uphill. A steeper hill is going to have a higher gradient. A kind of slope that has a lot less steepness to it is going to have less gradient. And this is the same thing here. How this is important is the differences of how high this high is versus how low this is going to affect how the air moves from one area to the other. So what makes the wind blow? When we take these air pockets and we take this air pressure and we put that kind of together, we get air flowing from areas of high pressure to low pressure. The greater the difference, or the greater the gradient that we just talked about in the air pressure between these two, the stronger or weaker that this wind will blow between them. So pressure differences and winds are caused by this unequal heating of the Earth's surface. Hotter areas have lower pressures, so more air is going to rush into them. Colder areas are going to have more pressure, so they're going to want to move into those low pressure areas. So measuring surface wind and direction and speed. We can talk about both current and future weather. Right now, if you're taking this class, you are a amateur meteorologist. We can use these guys here. These are wind vanes to determine the direction of the wind as you're driving on the highway. You might see them on barns. You might see them on houses. People have them. A lot of businesses have them. Airplanes. If you go to airports, they have the windsock, which is kind of the same. It helps tell the actual speed as well as the direction, which is kind of cool. The arrow will point in the direction the wind is traveling. This one conveniently has that arrow will kind of align with that northeast, south, and west. And winds are named for their point of origin. So if a wind is blowing from west to east, it is a west wind. It is a westerly wind because it's moving in that it came from the west. If it's an easterly, it would move from east to west because it was coming from the east moving west. To measure the speed of wind, we will use what is called an anemometer. And this is used to, it usually placed 10 meters off the ground, and it's used to figure out as faster that spins, the faster that the wind will be going. And usually a lot of these are tied to some kind of electronic component where it does the calculation for you and then pumps out a number. So we have whitecaps on waves in lakes and oceans at around 20 to 30 kilometers per hour. Your umbrella wants to turn inside out at around 40 kilometers per hour for wind speed. And then if we get up above that 90 kilometers per hour, that's when trees start to get uprooted, and you're going to have to be careful there. So, all right, our next section is about factors affecting wind and kind of how we get these different wind speeds and directions and how there's different kind of these factors occur. So if Earth was perfectly smooth and it was perfectly flat, we would have air that was just flowing in straight lines at really, really high speed. And all of that air would flow from an area of high pressure to the area of low pressure, and then we would have no pressure differences on the planet. However, this is not the case for how wind kind of happens on planet Earth right now. There is lots of curved winds. We have things like tornadoes and hurricanes that are big circular wind patterns, and this happens because of the shape of the Earth and the movement of it. Okay, the first thing we need to talk about is the Coriolis effect. And the Coriolis effect is the tendency of an object moving on Earth to curve away from its path of travel and not travel in a straight line. In the northern hemisphere, these objects will curve to the right, and in the southern hemisphere, these objects will curve to the left. And when we talk about weather in a subsequent chapter, we'll be able to tell whether a hurricane or like a monsoon is in the northern hemisphere or southern hemisphere based on kind of the direction that it is moving. So what are the effects of this? We already said, in the northern hemisphere, things are deflected to the right. In the southern, they're deflected to the left. The Coriolis effect is greatest near the poles and least near the equator. There's more area around the equator, and the poles are much smaller. The effect does not depend on the direction of movement, though. In this image here, both of the lines are moving to the right. If we swapped that and they were moving to the left, the things in the northern hemisphere would still be deflected to the right, and the things in the southern hemisphere would still be deflected to the left. You really notice Coriolis effect when we're talking about things moving a long distance over a long period of time. So if you were an international jet pilot, you would have to worry about the Coriolis effect when you were plotting and kind of going through your route. But because of the Coriolis effect, we get some wind directions based on the hemisphere that you're in. If you're in the northern hemisphere, these winds are tending to blow clockwise out of areas of high pressure and counterclockwise into areas of low pressure, these colder areas. Remember that high pressure means hot, low pressure means cold. In the southern hemisphere, this is flipped, and they're going to flow counterclockwise out of high areas and clockwise into low areas. So for most of the applications that we're going to look at, it's going to be most northern hemisphere centric because that's where we live, but we will mention some kind of southern hemisphere examples too. So with wind and the speed of wind, a big force is friction. Friction between the air and the ground, while it seems like, air should be able to flow through trees and over bushes and stuff. It does have to change its direction, and when it changes its direction, it slows down. So there is this significant force here of this friction that is slowing down the wind. Slower winds are deflected less from the Coriolis effect. So the smoother the surface, the faster the wind, the greater the Coriolis effect. If you're in a desert that has a much less topography, or you're in the middle of the United States where it's flatter and there's farmlands, you're going to have faster winds because there's not as much friction with mountains and trees and other kind of substances that are poking up off the ground. Where this is really significant is when you get really high up above all the mountains and above all the trees. That air is able to blow in pretty much a straight line because there's not a lot of friction happening there, especially above the mountains and really high up in the atmosphere. We call these really high, fast-moving belts of air jet streams. And they're moving very fast. They have very little friction with the ground. We have a tropical and a subtropical and a polar one. They're called jet streams because they're really good to travel inside of if you're on a commercial jet, because you are able to move very fast if you're going with the jet stream. If you're going against it, it slows you down. But if you're going with it, it does speed you up. These are usually thousands of kilometers long. They're pretty wide as well, kind of up 100 kilometers wide and about a kilometer tall. And depending on seasonality and current conditions on the planet, they can stretch in a belt all the way around, kind of like this picture is showing here. Sometimes there's breaks in the jet stream and it doesn't quite flow all the way around, but it does happen. We have a polar jet stream that happens it happens above the United States, kind of where the mix between the United States and Canada is. And it says this cool region here is mixing with the temperate air that's over most of the continental United States. This polar jet stream and how things are traveling through it and into it really affects weather in the United States. It supplies a lot of energy for storms. It kind of pushes them in certain directions. It moves fastest in the winter and slowest in the summer. And then we also have the tropical kind of easterly jet stream that's happening really kind of at the tip of Florida in the United States, across Mexico, closer to the equator. And this is much warmer air in the summers and the springs. This is the one that's going to be responsible for hurricanes and other kinds of wet weather there. The next thing we're going to kind of jump into is we're going to talk about global wind patterns. We've kind of been talking about things that are regional, or in like the case of the jet streams, can be global. But in certain parts of the world, we have very predictable winds and kind of wind behavior that we're going to see. With the United States, because we have cold air above us and a hot air below us, and we're a very big area, we have a lot of different kind of wind directions and changes that are happening very frequently. So the factors that affect this and kind of cause these changes are temperature differences in the heating of the earth, the time of year, And then the local topography, how much up and down that area has. The wind that we have over here, kind of in the Rockies area, is going to be a lot different than they have in kind of the Texas, Kansas, Arkansas area, or even the East Coast, which has the Appalachians, which are really small. So if, just theoretically, we could stop the Earth from spinning, we wouldn't have this Coriolis effect of these winds being deflected left and right. As the warm air around the equator, which is getting the most amount of sun, it would rise and it would move towards the poles. At the poles, it would cool down because there's not as much sunlight, and it would descend and kind of sink down, and that colder air would move back towards the equator where it would get warmed up again, and then continue this kind of circular motion. We call this circular motion a cell. And for this kind of example where the Earth is not rotating, we would have two cells, one cell in the northern hemisphere and one cell in the southern hemisphere, where all the air would rotate up to the poles, down, back to the equator, over and over again. But because Earth is rotating, this doesn't happen. We get kind of, there's this, the wind is deflected and it's not able to get all the way up to the equator, or all the way down to the equator, excuse me, or up to the poles because it's spinning around. So it's cooling and sinking way before it gets to the poles, and then it's heating up and, rising way before it gets back to the equator. So realistically, what our planet looks like is we have a 3-cell model, where there's 3 cells in the southern hemisphere and 3 cells in the upper hemisphere. And we're going to talk about each of these. This is kind of what this pattern looks like. And you can see that in the northern hemisphere, everything's getting deflected to the right, whether it's moving from right to left or left to right. And in the southern hemisphere, everything's being deflected to the left. Okay, so the cells that are in these different hemispheres are going to be the same, but just kind of a little bit different based on what the deflection is. So we have a cell between the equator and the 30 degrees latitude. That's the Hadley cell. We have one between the 30 degrees and 60 degrees latitude. That's the Ferrel cell. And we have one between the 60 degrees and the pole, which is the polar cell. And as this air is moving, kind of the direction of the air circulation changes. So why one might go up, over, down, the one next to it is probably going to go down, over, and up, and so on and so forth. So starting at the top, and then we're kind of working our way down. We have the polar front, and these circulation cells are caused by these high and low pressures. At polar areas, we have a lot of pressure because the air is cold, and cold, dense air results in a high pressure, where warm, humid air results in a low pressure. So we have this polar area, and it meets that kind of warmer 60-degree latitude where you have that warmer air rising, which is a low pressure area. And this boundary where this cold air is trying to flow into this warmer area is called the polar front. And this is important for weather. This is when we get snow, is when we have mixing of these two. And so we kind of like to watch the polar front and see what it's doing and kind of what's happening there. In addition to this, we have wind is kind of interplaying with this Coriolis effect here as we get northern air from the kind of flowing southward from the North Pole. It is going to the right, and as it blows to the right, it is going to kind of move from that up, down, up, over, down method, and then as it goes into the next cell, it will go up, over, down, and then the next cell, it goes down, over, up. And in the southern hemisphere, it's kind of reversed here. And this image here does a really good job of kind of showcasing this. As you can see here, if you were to follow like one individual chunk of air here, you go down, over, down, and then over, up. So it's alternating. So there are some weaknesses to the 3-cell model. It doesn't work everywhere on the planet. Not everywhere on the planet is exactly the same. We have continents versus oceans. We have big continents versus small islands. So there's some strengths and weaknesses to this model. It's very simplified and mostly looks at upper level winds. So we're not looking at things right on the surface usually because of all the friction and the uneven heating. It also doesn't really account very well for seasonal changes or for continental heating. So the continents are going to heat differently than the ocean. And where it really doesn't work very well is kind of this highlighted area on this map in the middle latitudes. And the reason for this is these areas change from high pressure to low pressure and back really quickly. A lot of times in the course of one day, or even several times during the day. If we get a rain, it gets colder and we get high pressure, and then we get sunshine as those clouds break up and we get low pressure. So there's a lot of change that happens in here, a lot. And being, as you can see in this image here, right smack dab in the middle of that middle latitudes area there, we get a lot of changes very quickly. Yeah, the only parts of the United States that aren't are most of Alaska and that little tiny tip of Florida down there. So some more weaknesses here. The continents are heating and cooling more rapidly than water. Remember when we talked about water, water has that really cool ability to insulate. So if it's hot, it stays hot longer, and if it's cold, it stays cold longer. The continents heat and cool very quickly. When it's sunny, they heat up really fast, and when that sun goes down, they cool down really fast. Some strengths of this model. It gives outside of the middle latitudes, we get some pretty accurate description going on here. So it works really good in the Hadley cells and the polar cells. It's useful for looking at climate studies. It's really useful when we look over long periods of data. You can see these changes in these kind of cells and how they change seasonally, which is really, really useful. Inside of these cells, we have certain areas that we call wind and we call pressure belts. And these kind of things have certain characteristics that were especially useful when we were sailing, but they're still useful when we talk about things like climate change and we talk about when we get to oceans and we talk about ocean currents. All these things will be super, super useful. So to start off, we're going to start off with the ITCZ, the Intertropical Convergence Zones, and we're going to talk about the doldrums and a couple kind of areas here. Most of these were named during sailing times, so they have some kind of cool naming mechanisms here. But the reason for this first one is the tropics are hot. They are hotter than most parts of the Earth during most parts of the year. They are constantly, each day, heated about the same. This creates a literally low pressure area right there along the equator. This low pressure area is called the Intertropical Convergence Zones, the ITCZ. What we're getting here is we're getting mixing from both continents and both hemispheres, and there's not a lot of wind, and we do get a lot of rain. Because there's not a lot of wind, this area was called the doldrums. And getting stuck here was usually not a good thing if you were a sailing crew, because you would make very slow progress, and being at sea for a long period of time when you were able to pack only a certain amount of food was not usually very, very beneficial. So sailing vessels often got stuck in these areas. Similarly, we have the horse latitudes. And this is between the areas of 20 and 35 degrees latitude. Air is sinking down here. And because of this, it has very little rain in it. And most of our deserts are at this latitude. You can see it goes through parts of Arizona here. It goes through the Atacama Desert down here. It goes through Australia, which has a lot of deserted areas. Parts of Africa here. We also call this area the horse latitudes because, and this is allegedly, cargo ships would get stuck here and they would throw the horses over the side to lighten their load. The reason for this area is really calm and dry. So once again, getting stuck here, sailing across the sea is not really what you want to do. Where you want to be is you want to be in the next area, which is the trade winds. So between these two areas of the doldrums and the horse latitudes, we have the easterly trade winds. And these are warm winds that are pretty steady. They blow the same direction most of the time. So because of this, they were kind of ideal trade routes for sailing ships. In the pole regions, we have kind of a different thing going on here, where we get the westerlies versus the easterlies, and we have these high pressure systems that are blowing in the same directions, and they're called prevailing winds. All right, our next and last section here is on continental and local winds. So we're going to take the big picture, what we just talked about, the really big, the entire globe, and we're going to now shrink it down and look at just small systems, things like continents, or even things smaller than continents, like being on a beach or being on a mountain, and how that affects your wind. So kind of starting big and moving small, Earth's position and our tilt around the sun creates the seasons that we get. When we're pointed more towards the sun, we get summer. When we're pointed away from the sun, we get winter. As the temperature changes, so does our wind patterns. The reason for this is mostly due to how the continents heat. The continents will heat faster. They create this large difference between the temperature of the oceans around them and the temperature of the continents themselves. Usually, the highest temperatures on Earth are not at the equator, but at the hemisphere that is experiencing summer. So that is where the biggest differences are, because the land is heating up a lot faster than the water, which is heating up much slower. The equator is more right around the 65-degree mark every single day. So they have a lot less difference, a lot less wind, and that's why we have the doldrums there. So in the summer, continents are really hot. Because of this, they have that less dense air pressure, that low pressure over them. Remember that hot means low pressure. And the ocean air is colder, meaning it's a high pressure. This wind is going to move from this high pressure ocean to the low pressure land. And so the wind will blow from the ocean onto the continent. In the wintertime, when the ocean is warmer and a lower pressure and the land is colder and a higher pressure, this is reversed. So in the summer, the wind is going to blow into the continent. In the winter, the wind is going to blow out of the continent into the oceans. With this seasonal wind shift, we can get things like monsoons. So these winds that are changing direction seasonally are called monsoons. We get very dramatic ones on the Asian continent. They get this total wind reversal, where we get the cold, dry air of the continent moving towards the less dense, warmer air over the ocean. They usually have really, really heavy rains when they happen. This image here is a great example. These guys are out during monsoon season, and there's a lot of standing water there. In the summer, we can get summer monsoons, where the low pressure area of the heated continent is now having lots and lots of wind coming in from the oceans. That wind is bringing lots of water with it. When this really, really warm, moist air reaches the higher regions, at the higher elevation regions, going up mountains and like going up the Rockies and going up the Himalayas, as it starts to cool, it dumps all the water out of it, causing lots of rains in areas like India and Southeast Asia and Portland and Seattle, and they get a lot of really heavy, heavy rainfall. Something that happens seasonally, that ITCZ, that intercontinental zone there, is it shifts based on the time of year. Because it's the area where the north and southern hemisphere converge, when these areas are moving more towards winter or less towards winter, this thing is moving with them. So as we have that tropical air in the summer moving north, the ITCZ moves north. So on this image here, you can see that in July, it's higher. It's going up into parts of Mexico, down into the higher parts of Brazil there, across most of Africa and into Asia. As we move into winter, you can see that this thing really starts to drop down. It goes just into South America, not into Middle Americas there. Lower in Africa, touching the tip of Madagascar, and then into the Philippines and even touching parts of Australia there. It doesn't move, and you'll notice on here, it doesn't move as much on the oceans, because the ocean temperatures don't vary as much, because all that water in the world's oceans are constantly mixing, and they have kind of different things going on there with ocean currents. Those ocean currents are taking those different pockets of different heated liquid and moving it around. The last kind of topic we're going to talk about are local winds. So these are winds that extend less than a distance of 100 kilometers. So they are things like the difference between land and sea breezes, mountain breezes, and valley breezes. Sea breezes can form along any coastline, not just islands. If you live on the Great Lakes, you get sea breezes. You get what we would classify as sea breezes. During the day, the land is warm and the air is lower pressure. This causes that cool sea breeze to blow inland, because that high pressure cold water is going to want to equalize, so it will blow towards that lower pressure hotter land. At night, this flips, and now that the water is warmer as it holds in that heat from the day and the land is cooled off, the water is the high pressure, the land is the low, and as you can see in this image here, that low pressure will flow towards the sea and the warm air will flow towards the land. So now we have the wind blowing into land at night. And this is a land breeze because it is moving towards the land. The other one was the sea breeze because it moved towards the ocean. This breeze is also cooler and denser because it's carrying all of that water as it's moving. And so that's what's going on there. So in the daytime, it's moving out towards the water. In the nighttime, it's moving back towards land. That warm air is. And then the last thing is important locally, especially for us up here in northern Idaho. We have mountain and valley breezes. So during the day, let's start at night. At night, we have the mountains are cooling. We have that cool air on top. That dense air sinks to the bottom, flows into the valley, and causes wind down in there. Because it originated from the mountain and moved down, it is called a mountain breeze. During the daytime, this flips, and it sends those air up instead. The warmer air goes up. It blows up from the valley to the tops of the mountains, and we call it valley breezes. Usually valley breezes are much slower, and remember that if it's slower, that means that there's less difference between the pressures. So the mountain ones, where it's that cold air moving down from the mountains, usually the valley's a lot warmer, and so it's moving much faster, and that's why we get those really fast, cold winds at night. Especially in this area, it can cause windstorms. So it's all caused by that unequal heating of Earth's surface. That's the conclusion of this chapter. I hope you learned a lot about wind, kind of understand a little bit more about global patterns of it, how seasons affect it, the different zones of wind around the planet, and how local winds kind of work because of this uneven heating and this topography. Thanks for watching. If you have any questions, let me know, and we'll see you in the next one.